secuBT, you can all use these things just as an add-on, and you don't really have to rely on the source level. You can do it for closed source program, you can use it for untrusted code that you downloaded from the internet, or for daemons that you're running to guard these. So one more demo I want to show you is how secuBT works with vulnerabilities. We have here a nice program that an undergrad student wrote. We have a main function, and well, this is just an excerpt out of that. We have some arguments, and we call a function, myfunc, and this myfunction takes the string and uses sprintf to print that string into a buffer which is only 4 bytes long. It's pretty clear that we can produce an stack overflow like that, override the return instruction pointer, and then do some evil stuff. So to make it a little bit more interesting, I didn't override just the return instruction pointer, but I used the return to libc attack. The exploit looks a little bit like this. We execute that evil program, but we add some specific string behind that. You see that the environment contains the LD preload. This is either the preload that we use for the binary translator or nothing at all, and some shell in the environment. And we'll use the system call, as the libc system call, to execute the program that is written in the shell variable, and then branch back to that. So if we just execute that, this is the same. We can look at that code. This is the exploit. We have here a little bit more program, a little bit more code, and in the end we just execute that. As I said before, we construct the system call, bring in the pointer of the shell, and execute system in C. And this looks a little bit like this. If you execute that, we pipe that into the program. The exploit code is placed. We execute it, and bam, we're in a shell, which is kind of a standard libc attack, which most of you will already know. But if we exit that shell, we will return to OX coffee, and the program will fall away. But on the other hand, if we use the LE preload fix that you see here, if we add LE preload as an argument, we use the binary translator as preload. We preload the binary translator, and if you execute it like that, exploit code is placed. We execute it. We currently disabled in the binary translator the return instruction pointer checking, so that it goes through and would execute bin bash to execute bin tcsh. So the guard sees that this is being executed and kills the program as it is not allowed like that. And while our security worked, the program is terminated and everything is fine. So we see that it works. There are many things that you can play with, and you can use secuBT for proactive security. You can contain and detect memory corruption, and you can add to a program additional protection without recompilation. So you can use BT or secuBT for two things. One of them is execution of malware or some unknown code that you downloaded from somewhere, and the other thing is to guard your server processes against unknown exploits, so proactive take on security. You can use the binary translator to support the full IE32 ISA without kernel modifications and add some user-space virtualization scheme around running processes. You can intercept all interactions of the program with the kernel based on system calls, signals, everything, and redirect these to your user space implementation to play around with different implementations and different things. So you can do a lot of stuff It's very interesting field, and if you're interested in, I would like some, this is all open source. If you're interested in, you can work on the code, you can download the code, you can experiment with these things, you can try to hack it, get around the security extensions, make it better. And with that, I want to finish. Thank you for your attention, and I'm open for any questions. Yeah?
Is it on? Any problems running multi-threaded programs?
No, it's all multi-thread safe. The binary translator, there are two different schemes. First of all, we wanted to run multi-threaded applications as well. That's why we implemented everything on top of pthreads and kind of hide these pthread things a little bit. So we have the code cache based on a per thread basis. This makes it also faster as well, because thread will kind of, then we have the locality effects for the different threads and everything.
I have a question regarding the code cache base address randomization. If the target program tries to hunt for your code cache and the kind of patterns that can be embedded with the code cache, which could be used to basically track it down.
Yeah, you kind of want to search for the code cache by kind of forking and then grabbing through the...
Or not even forking, but just looking through the memory.
Well, then you will have like an exception or a seg fault or something like that and terminate the program. Or did I get you correctly?
The code cache is located within the process memory, so basically you're not going outside of the own process memory, so you won't seg fault.
Yes. One of the forms, or we kind of worked with that, we kind of tried to locate the code cache as well. And the scheme we used was we forked the process and then kind of like, we forked the process, gave it a parameter, and this forked process always tried one page after another and kind of went through memory one page after another. And for a 32-bit address length, this is possible. But on the other hand, if you forbid the fork system call or limit the fork system call to specific locations, you can also forbid this kind of scheme to find the code cache. And otherwise, if you would just try to read random addresses, you would kind of have really a lot of seg faults, right? And then you could terminate the program.
Okay, thank you.
Okay.
Okay. How well does it interact with just-in-time compiling? We have browsers that just-in-time compile JavaScript. We have applications that embed Mono or Java virtual machines. How well does it work together?
Yeah, this is a really big problem. Currently, whenever we detect self-modifying code, we just kill the program. That's the easiest take on that one. The next approach, well, this is basically, it's a one-man project with some extensions, so it's really hard to implement these things. But there has been a lot of work with self-modifying code that has been done. And one of the takes, the easiest take, is to catch or to make the code read-only. And whenever the program writes to it, we catch the exception in the binary translator in the additional privilege level. We pinpoint the page, and we kill all code that is in the code cache for that page, and then we'll just retranslate everything. This is the easiest take, and other takes are then there are more sophisticated schemes that are possible. So it is possible to do, but yeah, currently we just kill the program. Another easy approach would be whenever there's a write into the user space, into the code, into the user space code, we could just flush the code cache and start translation again. This would be the easiest way to implement that.
Is there a special reason why you didn't use Valgrind as a translation engine? Because it is already there, and most of the problems the last asker is already solved there.
Yeah, we evaluated Valgrind as well, but it has like a 1,000 times overhead.